The broadcast is now starting. All attendees are in listen only.
Hello, everybody. Welcome to our Kiln Axis Survey webinar today. My name is Tom Zhang, Senior Engineer for Optimus Solutions, and I got here Mike Atwell. Why don't you introduce yourself?
Good morning, everybody. Mike Atwell. I'm the Director of Engineering for Industrial Kiln and Dryer Group.
And we also have Brent Stansel, the Eastern or the Southeast, Southern. Oh man, I'm just screwing this up. Brent is the Southeast District Manager, and he's on the background side. If Brent, you would like to go ahead and introduce yourself, you're more than welcome to. For everyone listening, some housekeeping. Try to make sure you can see us on the webcam. Sometimes we will show some stuff or have some discussion, and we want to show on the webcam side, like our rotary dryer. We've been doing something similar most of the webinars, so try to make sure you can see that. If you do have issues, we have a very good crew on the other side. Type in the questions in the question section, and they will help you out on the technical side. Throughout this presentation, if you do have questions, go ahead and ask, and either we'll pop up during the discussion, or we'll answer it towards the end if we have time. So without further ado, we're going to go ahead and continue. This, again, is a presentation on our Kiln Axis Survey service, and we'll go through details. So the first thing is, what is a Kiln Axis Survey? What it is a set of diagnostic measures for rotary kilns, typically 3 tiers or more, and it's a way to diagnose and show the health of the unit from a mechanical standpoint. A standard Kiln Axis survey has alignment measurements. This goes through our methodology with the different theodolite measurements that we have, ovality measurements, temperatures of the shell and tire, creep measurements, and a general inspection. So when you get a standard Kiln Axis survey, and if you call it and say, I want a Kiln Axis survey with nothing else, that is what you get, okay? And generally, it gives you most everything. We have different options, option 1, 2, and 3. These are add-ons that you guys could have, and these are specific problems that you may want to see, solve, or show quantitatively. So, for example, option 1 is our package using our inductive distance measurement tool. It measures gear runout axially and radially, assuming we have access, tire wobble measures, and dogleg of the shell through the tire, or the crank of the shell through the tire, okay? Option 2 is if you suspect there's a taper or it's got an odd deformation, tire and roller face profile. This gives you diameters across the face of the tires and the rollers. And lastly, the kiln shell profile measure. So this is the span of the shell. This plots out a nice 3D graph. And typically, if you have major deformations with refractors falling out and the span between the tire and tires, or the seal areas, this is a measure for that. Overall, this is our equivalent to a Hot Kiln Alignment. It's the new version of the Hot Kiln Alignment. Again, this determines the general health of the kiln mechanically. And again, it's a way to use data to drive decisions with shutdown repairs. This methodology uses what we call the prism axle method, where there's an axle with a prism, as you can see in that image. Mike and I briefly talked about how the measures go on this, and the evenness that we should get the diameters or the circumference as we measure. This has a wheel with a prism. Again, this has a wheel like the measuring wheel with a prism in the middle. And as we go through, there's ways we can check how we're doing a good job, et cetera, et cetera. The overall process, is that you got a problem, right? And Mike will get those all the time. There's a problem, and typically when there's a problem, we like to have a conference call or chat to see what it is. Maybe it's something that you're seeing that we may know more details of, or maybe there's something that we assume that you can clarify. Typically a conference call where you call us. This is a combined service of industrial kiln and drying optimist solution. So you're typically a conference call with the key account specialist or the right parties, the technical parties in mind. And we're there to figure out what the problem is and how to best evaluate that problem or diagnose that problem. It shows us what the best measures are. If you have a shell issue and you want to see data, we would recommend a kiln shell profile. If you have a loose tire that is high creep, okay, we could do standard, but maybe you would like to know more from a tire wobble sample, how loose it is. From that point on, we then communicate the problem that you have and the measures that you need to take with a crew that will be on site to take the measures. They will then be communicating that information, and before they leave, they'll typically call one of us in-house in Louisville. We'll do a review session with the customer the following day, and then they head out. Typically, the review session is your major points, and this is fresh data that's very obvious. Like, hey, you got a crank near the tire or at the tire at this spot. You need to consider a correction cut or a tire shell replacement. Here's why. Then after they leave, we do a written report with recommendations on the next step forward. The recommendations will typically be what you need to do, say, on the next shutdown, or any corrective actions or any monitoring actions you need to make. Then we can do a follow-up call to review the results and recommendations from the report. The major point here is that we will always try to have a technical data-driven discussion throughout the process. This way it's more quantitative, it's less opinion-oriented. We can interpret based off of the results, but the goal is, here's the data, what do you guys see on that? Any thoughts, Mike, on that? Sound good? When we started this journey, we looked at a lot of different alignment surveying methodologies. And there's about 7 or so that we compared in the market that is being used in the market. You have a shell-related measurement. You have the reflectorless measurements. Excuse me. You have other prism styles. But there are a lot of major comparisons on the market. The target axle methodology was relatively straightforward to implement and very accurate because you're using a prism versus something that you scan on top of the tire or the shell. Typically, reflectorless method is about twice as inaccurate as if you use a prism, and that is on the spec sheet itself from the theodolite manufacturers. The accuracy range that we try to adhere everybody to in terms of our crew before they leave site is a plus or minus 40 thousandths or overall 80 thousandths limit. These are limits on the fit of the tires, the station-to-station movement. The goal here is that any time a customer comes on site or comes and talks to us, or any time that the crew or the team communicates with anybody else, we can always show that overall you're below these magnitudes. And the reason why is there is a 1/8 inch, so plus or minus 1/8 inch or overall 1/4 inch limit. So we got to be more accurate than that so that it makes sense. Also, we are always exploring the latest and greatest, and we go through internally. So this is where Mike and I always debate on, okay, I want to use this. Why is it good? Why is it not good? Is it worthwhile? Can it be implemented? Is it practical? Is it cost justifiable? The theodolite was a no-brainer and had to be very accurate. The latest tool measurement diagnostics, we chat with our with the tool makers and see what they have, what's the latest and greatest, and can we implement. So our methodology is we cross-compare with other methods to see what's the best accuracy-wise and easiest to implement. We hold our teams accountable for the accuracy that they make, and we're always exploring the latest tech. And before we implement, we internally have a discussion to see if it's worthwhile.
I think one of the other big things you got to talk about here, Tom, is when we go out, and we can't shoot all the kilns from one side. So you got to move from station to station. Or every time we relocate the theodolite to a new station, when we shoot all the control points, the first thing we do is go back and look at the fit of all the control points at that station. If something comes up and the fit doesn't meet the requirements, we have to go back and readjust where we're reshoot their control points, try to figure out what might have moved, or if something has changed or somebody did hit a control point, we have to stop and start from scratch. But the whole way through, we have to go back and check the control points prior to shooting the unit. And when we get done shooting the unit at that station, we check it again before we actually tear it down and remove it. That way, if something happened to the theodolite where it was at, if it got moved or shifted while you're taking your shots, and you shoot your checkpoints again, and it's out of the calibration of where it has to be held, we stop and redo all those shots from that location.
Absolutely. And this is where we check it fundamentally throughout the process. And also what's really good is we can see it now pretty easily, because once we change a station from one side to the other side, it's almost immediate if something's bad or not. We're also very conservative on making sure that we have margins for error.
And the other thing that's on this is the guys out there, every shot they take, every time they check the control points, it's data logged. It's there. It's a permanent record of what is turned into us. So if we go back later, we can look at their control points and look at their different locations of the stations and find out how accurate were they. And we can quiz them on that. Or if we look and say, hey, there's all the shots at this location turned out bad and you guys missed it, and we can go back the next day and reshoot it.
Right. We have ways where we can check the integrity of the information, and it's actually built into our methodology. I always strive to show that we can do a good job, or I guess I always strive to answer the question on how do we know we're doing a good job. And the examples that you guys are seeing on the right of the images, these are all under 40,000s. And these are ways that we can double check and triple check. By the time we leave the site that day after the shot, the team already knows that this is good. And I think that's a very important piece of the methodology that we have, is that it's very, very accurate, and that it's accurate and the team is held accountable to doing the best that they can. So I've been very happy with it, because now versus some of the other methods, you don't really know if you've done a good job until you sit in the office. So why do all this? Why do a survey? Well, again, the major point here is it's a quantitative assessment of what repairs need to be done, or if any repairs need to be done. And these are things we're going to talk about on each. Misalignment adjustment. You do a survey. You don't want your system to be misaligned. Think of a straw and it kink, the straw with that little bend, you know what I'm talking about, Mike, with the milkshake bendy straw. You want to make it where it's straight as possible. If it is bent, if you have 3-pier and pier 2 is misaligned, you run into the arena of circumferential cracks if it's too high of a misalignment. If you are considering a shell replacement, or if you've been told you need to do a shell replacement but you haven't had data, this is a way to show the data. Same with planning for a tire repad reshim. This is where if you have an inch creep or 25 millimeter creep or more, you would like to know that. Or we have that discussion on, is this a different point of your process? Is it winter? Is it summer? Are you running hotter than normal? Or are you running cooler than normal? refractory monitoring, this is where the ovality comes in. If you've got high ovalities and you are losing brick, okay, now let's look at why. Is it because the refractory failed? Is it because on the discharge end your burner is adjusted to where it's deteriorating refractory, or is it insulation, etc.? And then dogleg crank at the tire or at the shell through the tire. That's a highly consequential phenomenon. And some of the future things that we've done is how do we feed some of this data, some of the alignment data, to where we can simulate loads. So that's another interesting thing that we've learned now. So misalignment. Again, plus or minus, so you guys see on this, there's two graphs, or there's two figures, a horizontal misalignment and a vertical misalignment. For the horizontal misalignment and the vertical misalignment, the limits that we have is plus or minus eighth of an inch. So plus eighth of an inch and minus eighth of an inch, so 0.125. Why? It's an industry rule of thumb that we've used. On the vertical, it's actually a little bit higher, but we like to stick with a more conservative misalignment set. But we've also started modeling misalignment in our FEA models and have shown that this hits close to the 3,000 PSI limit on the shell. So we have now verified that you really want to stay within this from a fatiguing standpoint, or ultimately a circumferential crack over time. So when you're within this limit, an eighth inch is not much. It is. It's tiny for what, a 10-foot, 15-foot, 25-foot unit? It's pretty small. So ultimately, if we shoot the unit with the methodology that we have and it's all within, we would consider that relatively aligned. Any comments you want to make, Mike? Okay. The second one is a shell replacement. So the rule of thumb in the industry is if you're above, say, half an inch run out, so 12 millimeter in this chart or 15 millimeter in this chart, you need to replace shell. Okay? Well, before we just go replace shell, we need to talk about it. We need to measure it. We need to learn the history. So this is where the experience of, say, Brent and the different district managers or the people in the field, we use that experience and we use the customer problems to see why. So, for example, this particular unit, we didn't measure the full unit. We saw that the tire had, the customer wanted to repad the tires. Repadding was done about 8 months ago, and then the pads or the shims got loose, and then repadding was done again, or they were considering a repadding again. So our view was, okay, hey, we have to repad, and you already considering a repad in 3 months, 4 months, something's off. So we did an investigation into it, and we saw that the shell under the tire was, it seemed, profiled or shrunk in where there's a big divot. So we talked with some of our internal groups on, hey, there's a divot. You probably need to replace the shell in this section. So we said, okay, before we say just replace the shell, maybe this is more than just that spot. So this is where the runout, the shell profile measure comes in. We measure it, and it was much more than the tire section. It was roughly 50 to 60 feet with the deformation that we saw. You see as high as 37 millimeters or inch and a half to 2 inches, or yeah, about an inch and a half or more. And we saw dark spots. So it seemed that the shell was heavily heated above the temperature that it needed to be. So you got temperature issues, you got pad issues, and then the shell replacement was just that quantitative data that puts a ribbon on it to where you need a replaced shell. Not only that, but those of you on the line considering changing shell, you have to justify it with your capital group. Or if you're the capital group, you have to justify it because a shell replacement is not cheap. So by thinking through in this way, by seeing the experiences and the history with the unit and the quantitative data, it makes a very easy decision to do a job like that. Tire, repad, reshim. Typically, rule of thumb here is an inch per rev on treat is when you would consider a repad, or at least start planning or start discussions on one. When you do a repad, I always make sure or we stress to have temperature measurements with it, because with creep, it's dependent on temperature and dependent on wear. The temperature, and ultimately what it is it's the size difference between the tire and ultimately the pad shell, okay? So if the shell shrinks, you're going to have naturally a bigger gap, which naturally will mean there's a bigger creep. If you have wear, that naturally just decreases over time. So this is where we take temperatures and we ask the customers, hey, this is part of either the discussion before we leave or the discussion after we send the report on, hey, on the temperature, is this about normal for you? Is this cooler? Is this hotter? And most of you, I would stress to take creep measures because that's something you guys can do now. We just do it as part of the service while we're on site. So for this example here, Tier 3, the creep is 2 inches per rev. We also see that in Tier 3 that the temperatures are relatively tight. It's relatively low, okay? So when I see high creep, I typically, if it's temperature related, you see a high temperature difference. This one's actually relatively similar. So there is a very, very clear interpretation that this is wear related and temperature related. So this is how we would discern this value here. Any comments you want to make on pads, Mike?
No.
Okay. Okay, so ovality. So ovality is a measure where you're ultimately measuring the curvature and the deformation of the shell locally as it rotates around the system. The ovality location that's relatively low is typically at the very top here of the kiln, and the ovality with the highest deformation or highest change is typically where the tire shell meets the rollers. We try to make a relative, we have the core data where it shows the deformation, but I like to have a graph like that to show at least the upper limit. So for this case, roughly your Tier 1, Tier 2, Tier 3 are relatively good. Tier 4 may be high. This is where it may be specific to the industry. If it's refractory lined, it's that location on Tier 4. Okay, you need to go ahead and monitor that. If it's an industry, say, pulp and paper where there's chains, okay, you need to monitor it, but now make sure that it's not so high that you start having what we call axial cracks. Instead of circumferential, axial is this line and this way, circumferential is around the unit. So with axial cracks, you want to be more cognizant of that. Okay, so we arrive at the crank, okay? So with the dog leg crank of the shell through the tire, I would like to talk a little bit more about this. So when you have an area where it's got a crank, you can see something on the right where it's got a deformation on it. The idea here is if you see this phenomenon, you'll see it lift off the tire or off the roller, or the roller stops moving. That means there's enough deformation at the shell where it's lifting the tire. So when you have this, you have on the top right area of high load on the far left and far right, and almost no load in the middle, and a reduced load in the left and right, and a high load in the bottom. Okay, I don't think I've seen it, but I've never seen a kiln lift off of Pier 2 only, so that's why it's reduced load. This is a measure we do called the roller shaft bending measure. It's option 1. When you have a crank like that, and it goes up and down over time, you would have fatiguing of the rollers, the bearing, the base, and the piers, and it's a relatively expensive fix. What's that, Mike?
I mean, we've seen bases 1-inch plate, 16 inches across, just snap.
Yeah, it's a lot of load.
We've seen bases break off the piers and crack up the pier tops. So, I mean, there's a lot of forces going on, depending on how bad the crank is that you have going through the pier top.
And it's not an inexpensive fix. We have customers that think there is one, and they'll see that, and we'll measure it. But also, if we go through a standard survey and we don't see misalignment issues, we don't see ovality issues, this is a measure that I would recommend. It's also a very fast measure. It's a day, and you can get year and tire wobble measures. I would always recommend something like this, especially for 3 piers or more. So there's 2 values that I look for. On the left, you see the roller shaft bending values. Okay, and this is measured at roughly the 4 or 5 o'clock, or in that 30-degree angle under the roller. Okay, so you got the tire, you got the rollers. So I'm going to go back. You got the tire, you got the rollers. It's measuring, if you guys can see my
180 degrees from the contact point.
Yep, 180 degrees from the contact point. So we measure it here, okay, with the instrument. You'll get a number, and that is the deflection on the shaft. Anything above 0.2 is considered an alarm or something where we need to seriously look at corrective actions. When you have high loads and low loads, your peak to peak differences should be roughly 180 degrees, as you can see on the bottom. Say, for example, at the bottom, we'll see Pier 2, 300 degrees, bottom is about 125, so that's roughly 180 degrees apart. If I see the angles are not right, the roller shaft bending high, this would be a classic crank of the shell through the tire, something that looks similar on the right. You don't typically want to ignore these because when it does fails catastrophically, it's, like Mike said, you can break a lot of stuff, okay? I think, Mike, you had a point you want to make on the pier sway that you want to chat about.
Yeah, on the measurement right now, what we're trying to measure is how much the roller is being compressed or bow in the roller shaft. If your pier is not substantial, some of the piers are actually rocked back and forth. They're basically rock on their foundation. If the pier is swaying with each revolution, and it's pushing on the right roller goes to the right, or pushing the left roller goes to the left, then you're not going to build up enough pressure to actually see any deflection on the roller itself, because there's nothing to push against. So a lot of times you can have a crank and not really see anything breaking, but you actually, if you stand back, you'll be able to watch the pier sway, or if it has, depending on how the pier goes into the ground, sometimes you see a crack between it and the ground, or between it and the concrete around it. And when it rains, you get water washing in there. And then as it sways back and forth, you see water being squirted up out, or coming out and going back in. In other words, it's how much the pier is swaying.
Right. So even with pier sway, if we see the values are high, then it's a crank. If there is pier sway and we see like Mike said, the water coming out or cracks at the pier itself, and the roller shaft bending is relatively low, we still ask the question on, is the pier sway hiding that information, because it won't be as dramatic as if you were sitting on a rigid pier. So that is a consideration we try to make. We try to have that discussion because typically this one is consequential. This one, in order to correct it, so the question is, how do we correct it? A correction cut, you're trying to relieve that bow or the crank at the shell to get it to where it's straight at one location. This is different than alignment, because alignment is pushing the tire itself. This one is just the natural deformation of the shell if you were to align everything. Or a tire shell replacement, because it's, or tire shell roller bearing base tier replacement if it does cause the damage. Okay, so this is one of those where we need to consider that. Reading through something right now. Okay, so overall, some of the new things we're going with. You can have high deflections. You can have high loads. Okay, you can have altered the loads. Okay. And that is if you change refractor from, say, 6-inch to 9-inch, or you change chain, or you've added dams at various locations. On a load study, when we do a static load study, we consider those, and we try to keep it under the Hertz pressure that we have, the tire bending stress that we have, and the tire values that we all are considering industry standards. What we're doing now is we're integrating alignment information on these load studies, and it's the same time frame because we got more efficient at it. And anytime we do a load study, we will incorporate something like this with our alignment data, or if we verify other alignment data, we'll integrate this in. When we misalign and you have high loads, you will typically have far more amplified problems than before. So we did this particular study. We saw that the shell was high, as you see on the right picture on Tier 2, the reds. And this was after the fact. So I did this group, I did the alignment and the load study about 2 or 3 years ago, and we've asked to make the adjustments, and the adjustments were not made. So the consequence of this is they had a crack at that location, and we went back and we just used the numbers, and we discussed with the customer, and they said that we are actually, in fact, very accurate in the sense that they had cracks at that location. So, and there was circumferential cracks. So again, this just further shows that you want to make sure it's aligned. You want to make sure that the details of the alignment are there to where you don't get circumferential cracks. If you do, circumferential cracks are hard to deal with. When it's hot and it's rotating, if you don't catch it within 30 minutes or so, or stop the kiln immediately, you will have more than one kiln. Okay. Okay. So, overall summary. And once I do the summary, we can go through any questions that you guys have. So feel free to go ahead and start typing in questions. If not, we'll go ahead and just have a general discussion on different experiences that we have. Okay, so everyone has an opinion, okay, of what needs to be done on your units, and a lot of times it can get pretty frustrating because you get, quote, experts that tells you what needs to be done. The goal here, the thing that we strive to do, is how can we make data-driven decisions to help do the repair. If we can communicate to the customers or you guys, and it makes sense, and there's a logic, and there's data, and that what we say and what we suggest makes sense, then when you either get the capital project or try to get the capital project and or we finish the actual repair, we have something to go off of, whether it's a successful repair or even not, because it's data-driven. The idea here is if you have 2 or 3 different people telling them their opinions, hey, it's this and you need to go do this, and it's not something, and it's something that we can measure, and you're not getting that extra piece of information to give you the warm and fuzzies to move forward, because these are not lightly taken decisions, as you guys all know, especially if you're in the trying to get approval with capital. Our process, again, is fundamentally always going to be technical and data-driven again. There's a technical guide going through the entire process, making sure that it makes sense. We back-check each other. So if I see something that, normally it's this data set, but this time it's not, then say I would talk to Mike and go, hey, Mike, this doesn't make sense here. Did we screw up the measure here, or is it the measure itself? And this is where, especially if the crew's on site, I'll be like, hey, guys, why don't you take another stab at this particular measure, because we want to make sure it's as clean of a measurement before we leave. Once we go, okay, this is in fact not normal, then we start down the path of what it is and how to help. If we don't have the facts, if we don't know, and the data is different, then we will stick that. Hey, this limit is a rule of thumb we use in the industry. Hey, look, this limit is not a rule of thumb. This is a limit that we've calculated and we've verified, because that matters, because rule of thumbs have limits, and even analysis has limits. Rule of thumb is more empirical. Hey, over the last 50 years with 6 or 7 different OEMs or plus 6 or 7 service providers, we've come up with this number, and it hasn't failed yet. Okay, great. Or it's, hey, we put this into the model that we have. We've cross-compared with the data that we see in terms of in the industry, and we can prove it with core first principles or numerical engineering principles, and I would move that into a realm of this is a limit now versus a rule of thumb. And if we do that, I think it puts us in a stronger position. We know that there is a lot of knowledge that has retired out of the industry. You get a lot of new people that may not understand the fundamentals as much, especially if you just got hired. And this is what we're trying to strive to do is we have contracts that have retired and they have rules of thumbs, and now the next phase, the next iteration, the next thing we want to do is to move it from rule of thumb into a fact. So again, that's our general philosophy is overall set. Okay? So let's see if there's any questions. Let's see here. Let's see. Okay, so we got a question on why we include the gap existing between the tire ID and the filler bars for alignment calculation shots differ from the old alignment to shoot the descriptive shot. Okay, so in this case, we shoot the tire. Okay, we shoot the tire. Okay, and if you have very, very high creep of 2 inches or more, there's more of a gap. Okay. In terms of the methodology, the only way to get the shell is directly measuring the shell. Okay. Even the old methodologies or cross-comparing, so 1 out of the 7, the methodology measures the shell. The rest of the methodologies measure the tire. So comparing it to an old methodology is not relevant because it's still measuring the tire. Even if you do the method where you measure the 6 o'clock, 3 o'clock, and the, or 6 o'clock, 3 o'clock, and the 9 o'clock, that is still measuring the tire, not the gap. The issue with measuring the shell is not straight. The shell is not perfectly round. The shell deforms. So if you shoot, and also measuring the shell is incredibly bulky. The method I saw, you had 3 different lasers that you have to shoot uphill and downhill of each section. So from a practicality standpoint, that is not a good system because it's just bulky. This way, we can actually do it relatively quickly. So to answer your question on why we don't, it's the best that we can do where practically we can get data. And this is where if you have high creep, we would consider having that discussion on it. And this is a great discussion point that we can take where we internally see what the calculation set shows. The other caveat on this is that if you have a gap at the top of the tire to the shell, it raises or naturally lowers the unit. You have more play when you have a vertical problem than horizontal because of your system is meant to bear higher loads. So this is another point that we can go through in detail. Any other thoughts that you want to share, Mike?
On a tire, you got a nice, basically machined surface that is nice and smooth. That gives you nice, good measurement points. Or on the shell, you got the C mode, you got other pieces of equipment sometimes in the way. If you have a hot spot, which happens around some of your earlier Pier 1, Pier 2 things, your shell ballooned out, your shell could be Coke bottle. There's a lot of things that go on along the pier or on the shell itself.
Right.
So measuring the tire, and the shell basically nests inside the tire. That gives you a nice clean point to measure.
Right. And also, when the shell leaves the manufacturer, your tolerance limit with the shell is plus or minus eighth of an inch. If our tolerance and accuracy is plus or minus, or if our tolerance for misalignment is plus or minus eighth of an inch, you have a little bit of runout on your shell, and it's effectively not even worth measuring because your oscillations and your deformations, like Mike said, are already exceeding all the limits anyway. So it takes that measure as a possibility out to where now you have the tire measures, and we can use the gap, and we can use finite element, and we can use a different system to measure it. But otherwise, it's typically not as consequential as it is. Hopefully that answers your question. Anything else you want to add, Mike? I think that was a good question, though.
I think going back to one of your statements about, the shell, on some of the shell sections, they have a limit of 3,000 PSI. And basically, when you design a shell on these kilns, and it changes for different locations on the shell. We've gone, Dr. Seefe has gone back through and looked at all the fatigue numbers. And basically, where that 3,000 comes from is actually the fatigue life of what you can stretch the shell for lifetime drawings. When you put your unit out of alignment a little bit, your unit's already seeing 3,000 PSI, fluctuating, plus or minus, as it's going from top to bottom. As you move that out of alignment a little bit, that's adding to that 3,000. So now you're actually exceeding the 3,000, fluctuating. Which then gets you down into the point where you're going to get the fatigue life's going to show up at so many cycles. So, you try to figure out exactly when it's going to break. We don't know, but we know once you get up in that range, you're basically going to have a finite life to that shell. It's going to break at some point.
Right. And the general thing on the general limit there, ultimately is still a rule of thumb. We're actually actively trying to figure out where the 3,000 PSI comes from. Same with tire ovality. In the industry, I would say just about everybody, I know for sure 3 OEMs and some of the larger cement groups reference Nee's equation of 0.20% ovality of the tire. So how much the tire is changing from a perfect circle to a not perfect circle. That is assuming there is zero gap between the tire and the filler bars, and that it has even pressure circumferentially throughout. What we're learning is that that's not how that works. It's a saddle effect. So is the 0.20% overly conservative? These are the questions we try to ask. These are the questions we try to make sure that the limits that everybody assumes that we adhere and keep everyone accountable. so that it's not just, oh, do this because everyone says it works. My view is always, yeah, sure, everyone says it works great, but how can we show that? How do we go back to the first principles in engineering and show that? If we can show that, then absolutely. If we can't show that, then we have more homework to do. As one of the philosophies that we have is we are constantly trying to figure out what the rules of thumbs are and why it matters and why and how that truly affects your system. And then ultimately it makes us all better. Okay? So overall, I appreciate the time that you guys had. You can contact us at www.industrialkiln.com or optimussolutions.com. Number is 877-316-6140, and you can email, or if you guys have deeper questions, you can email at contact@industrialkiln.com. We're an essential business, so are we. We're open and ready to help. So without further ado, stay safe, stay healthy, and stay sane. And we appreciate it. Thank you, everybody.